Okay, this is a supplement to the lecture we had on partial fractions. Filled in a few details here. This current example that had the 4 factors in the denominator, each one was linear. All we really did in class was show how it would be written out with a over x plus 1 plus b over x minus 2, etc. I just wanted to point something out. When you have all linear factors like we do here, you can go ahead and get a common denominator like we did and then equate the numerators so that 3x cubed plus 2x minus 6 equals, then over here on the right we have a sum with 4 terms. Each term has either a, b, c, or d in it times the other 3 factors that weren't present. You can multiply all that out, excuse me, but there's a faster thing you can do when all the terms are linear, and that is, notice that this equation has to hold for all values of x. In particular, if you choose some strategic choices for x, a lot of the terms will be 0. So for example, letting x equals -1 here will cause this term to be 0, and this term to be 0, and this term to be 0, because each of them has a factor of x plus 1 in it. The only one that's not 0 is the one with an a in front of it. So we can plug -1 in on the left-hand side. We did that over here, and I think we get -11. Plug -1 in to the first term on the right-hand side, and we get a times all that stuff. And just like that, we got that a equaled -11 over 27. Similarly, we could plug in x equals 2 for b, or sorry, x equals 2 in the term that had a b in the numerator. And then all of them will cancel out except for the term right here that has a b in it, and so on. Here you could let x equal -2.5. Here you could let x equal -1/4. So you have 4 different substitutions you can do it one at a time, and you would get those variables. Another example we did in class kind of used a combination of methods. We started off and we just took this. I showed you how to factor the denominator, and we got a over x minus 2 plus bx plus c over x squared plus 1. And I think we stopped at that point. And here, when you equate your numerators, you get I called this equation 1. 7x squared minus 7x plus 1 has to equal the numerator here. On the right-hand side, we could notice that if x equals 2, that will all be 0 right there. So letting it down here, I showed it. Letting x equals 2, you get a times 5 on the right-hand side plus 0. That's right here. And on the left-hand side, when you plug in x equals 2, you get 7 times 2 squared minus 7 times 2 plus 1. You get that 15 equals 5a, and immediately then you know a equals 3. Then, if we multiplied out all the terms like we had done previously, that other method, and collect coefficients, we get that the 7x squared equals ax squared plus bx squared. That means that 7 equals a plus b. But we already said that a equals 3, so therefore 7 equals 3 plus b, and b equals 4. Similarly, from the third equation, -7x equals c minus 2b times x. You can go up there and look by equating the linear terms. Here we have a cx minus 2bx, and there we had a -7x. So -7 equals 3 minus 2c. I put the 3 in for b. Oh wait, sorry, we double check that. bx squared plus cx. 7. Let me pause a second. Okay, I corrected my mistake. I had mistakenly plugged in 3 for c instead of 3 for b. So this should have been c minus 2b. So we plugged in 3 for b. -7 equals c minus 2 times 3. That gives us c equals -1. So a was 3, b was 4, c was -1. Plugging that back up into our original expansion, we get this 3 over x minus 2 plus 4x minus 1 over x squared plus 1. I went ahead and integrated that. We get a natural log there. We could split the numerator into 4x over x squared plus 1. That just becomes a u substitution, so we get 2 times the natural log of x squared plus 1. And then 1 over x squared plus 1 is arctangent, and so that finishes that example. And I'll go to a new document for the supplementary notes. Okay, now I started a new notes. These are examples that were not at all started in class. Just 2 examples here. An additional thing on partial fractions that I didn't really mention in class is that when a factor in the denominator is repeated, all possible powers of that factor have to appear in the partial fraction expansion. So here's an example where we have this factor x in the denominator and it's raised to the 3rd power. So that means when we write it out, we need to have an x to the 1st, an x to the 2nd, and an x to the 3rd. They all have to appear. And then the x minus 6 is a linear factor by itself. Okay, now this is just a linear factor, but it's raised to a power. So when we get our numerators, the numerators will still be just constants, a, b, and c, respectively. And then there's the expansion right there. I got a common denominator. Notice that the common denominator is x cubed times x minus 6. So I respectively multiplied a, b, c, and d by whatever I needed to get a common denominator. Again, we used that trick before where we noticed that if we let x equals 0 and x equals 6 in the numerators, we can get 2 of the variables very quickly. Letting x equals 0, on the left-hand side we get 12, and on the right-hand side all the terms are 0 except for the c times x minus 6, and that gives us c times negative 6. So 12 equals c times negative 6. We immediately get that c equals negative 2. The other value that works well is plugging in 6, and when we do that, on the left-hand side we get 36, and on the right-hand side we get 6 cubed is 216d. So d is 36 over 216, which comes out to 1/6. And once you have those values, multiplying everything out and collecting terms, the x cubed term, there are none of those on the left-hand side, so we put a 0, right? It was 4x plus 12, so there were 0 x cubes. And on the right-hand side, the x cubed term was ax cubed plus 1/6 x cubed, because d was 1/6. So a plus 1/6 had to be 0, so a is negative 1/6. Similarly, there were no x squared terms, so we put a 0 here, and when we get the coefficient over here, it was negative 6a plus b. We knew a was negative 1/6, so that gives us that b equals negative 1. And now we have all 4, c, d, a, and b. I did go ahead and double check the constant term and the linear term, and we just got identities. 4 equals 4, and 12 equals 12. That just confirmed that we had been correct. We already knew that b was negative 1. Okay. Then you could write that out. And here's the integral. I didn't bother finishing evaluating it. And then the last problem is, this is one on the outline. I said, what would the partial fraction expansion be? I'll just show you this here. Here was the problem, 1 over this big denominator, and there were a couple of repeated factors. So this x plus 5 to the 3rd has to appear as an x plus 5, an x plus 5 squared, and an x plus 5 cubed. The denominators are what I just said. The numerators are linear factors because the factor itself is linear. On the other hand, the x squared plus 4 to the 2nd power, this is a careful distinction, that's a quadratic. So our numerator has to be, here's our first one, x squared plus 1 to the 1st. Our numerator has to be a linear term, ex plus g. And then, I have too many of those. Let's see. This is an x squared plus 4 right here. Okay. Then this one, hx plus j, using more letters of the alphabet, that's x squared plus 4 to the 1st, and then we need an x squared plus 4 to the 2nd, because that one appeared twice. Okay, this is a mess. I'm not going to even try to solve for those letters. This was just to illustrate the kinds of things that what can happen. In theory, it's very doable. Maple can do it very quickly, and I urge you to try that out. I'll show you in class how to use Maple. All right, I'm just in under 10 minutes.